Imagine launching a massive marketing campaign. Traffic spikes, thousands of users hit your application at once, and suddenly, your entire system goes dark. The culprit is usually a structural flaw called synchronous communication. This happens when two parts of a system, like a buying service and a shipping service, are linked directly together. The buying server sends a request and must wait, frozen, for the shipping server to respond. If that massive wave of user traffic overwhelms the shipping server, causing it to crash and return a timeout error, that failure doesn't stay isolated. Because the buying server is locked in a waiting state, the error travels straight back up the wire. The buying service is pulled down with it, and your entire application crashes. You might try to fix this by buying bigger, more expensive servers to handle the load, but throwing hardware at the problem only delays the inevitable failure. The structural dependency remains in place. To survive at scale, modern cloud architectures abandon these direct, fragile connections entirely. Systems must be built so that if one piece struggles, the rest of the application degrades gracefully instead of collapsing. The solution is asynchronous decoupling. Instead of linking services directly, we break the connection and place a buffer in the middle. In AWS, this buffer is typically Amazon Simple Queue Service, or SQS. When that massive wave of new orders hits the system, the buying service doesn't talk to the shipping service at all. It drops the requests into the SQS queue, where they stack up safely. Now the downstream shipping service acts completely independently. It pulls messages from the queue at its own steady pace. The traffic spike is completely absorbed by the queue, insulating your servers from overload. Sometimes you need to send a single event to multiple downstream services simultaneously. For that, AWS provides Amazon Simple Notification Service, or SNS. Think of SQS as a pull system for queuing data to be processed later, while SNS is a push system designed to instantly broadcast alerts to a wide array of subscribers. By severing these direct connections, you create a highly resilient architecture. But breaking a monolithic application into dozens of independent floating pieces creates a massive new challenge. You lose visibility into what the system is actually doing. When an error occurs in a deeply decoupled application, finding the exact point of failure is like looking for a single bad line of code across a dozen different machines. You need a centralized vantage point. That vantage point is Amazon CloudWatch. It acts as the central observability hub and the eyes of your AWS environment, designed to monitor resource performance. Directing attention to the first panel, this line graph demonstrates CloudWatch metrics in action. These are numerical data points collected automatically from your AWS resources, tracking exact values like the percentage of CPU utilization on an EC2 instance. CloudWatch also tracks financial telemetry, providing a real-time visualization of your overall AWS monthly spend. Directing attention to the second panel, the second core feature is CloudWatch Logs. This panel aggregates a scrolling stream of text-based diagnostic data, capturing the actual print statements and error codes generated by your applications. By pooling logs from all your disparate EC2 instances and Lambda functions into one searchable database, engineers can trace a single request as it hops between decoupled services, without ever logging into an individual server. Metrics and logs give you perfect passive observation, but if a critical failure happens at 3 in the morning, passively watching a dashboard isn't going to save your application. Directing attention to the third panel, this chart shows how to turn telemetry data into automated action using CloudWatch alarms. Here, we've set a strict red threshold line across a monitored metric. An alarm constantly evaluates that underlying metric and transitions between 3 specific states: OK, insufficient data, or alarm. If the data line spikes and violently crosses your defined threshold, the state shifts immediately to alarm. Once triggered, the alarm executes automated remediation. It can fire an action off to an auto-scaling group, instantly spinning up duplicate servers to absorb the sudden surge in traffic. Simultaneously, it can trigger an SNS push notification, instantly ejecting a high-priority text or email alert to wake up your operations team. CloudWatch alarms bridge the gap between human observation and machine-speed response, automating the recovery process to ensure your infrastructure scales without manual intervention. This creates a robust, closed-loop ecosystem. Traffic spikes are safely buffered by SQS and SNS, while CloudWatch oversees the performance and triggers automatic scaling precisely when necessary. There is one final piece required for a professional deployment: strict governance and security guardrails. While CloudWatch tracks the performance of your system, AWS CloudTrail acts as the strict auditor of your account. CloudWatch asks, "How is the system performing?" But CloudTrail asks, "Who exactly made the API call to change this configuration?" And to ensure all this back-end communication between your queues, notifications, and monitoring tools is secure, you deploy VPC Endpoints, keeping your traffic strictly on the private AWS network rather than traversing the public internet. Understanding how these specific services interlock, using decoupling for resilience, telemetry for visibility, and auditing for governance, is a strict requirement for proving foundational cloud competence. If you are preparing for your AWS Certified Cloud Practitioner exam, you will be tested heavily on recognizing these exact architectural patterns. Mastering these tools marks the transition from deploying fragile, entry-level applications to designing highly available enterprise-grade cloud systems.